Hi, everyone. Thanks. I'd like to thank the organizers and Gediminas for giving me the opportunity to talk about this. And this is some research that we've done with Juliana Orso. Let me see where this thing is. Yeah. Juliana Orso from Paris and Kuba Zakrzewski from Krakow. And I'm very glad to be speaking in the same session as Tilman Esslinger because although maybe he doesn't know this yet, this is all based on analysis of one of your experiments from some years back. Um, but we never actually sort of contacted you initially because we weren't sure whether we had anything sort of important to say. So before we sort of took up your time, we were just sort of trying to see what we could get with this. So I believe this is the experiment that Tobias Donner uh, runs on cavity bosons. So what we've got is there's a Bose-Hubbard lattice inside a cavity. And so the model that we looked at, this is based on this paper from 2016 in Nature. What we have a Bose-Hubbard model on the 2D lattice. Well, what the experiment has or had, right? And it's coupled to one cavity mode in the model, one boson cavity mode. So we've got the Bose-Hubbard model here of interactions U and tunneling J. Cavity energy once you take away sort of the rotating stuff, and there's a coupling between the cavity and the bosons on the two-dimensional lattice in a form here. There's this delta, which is like a checkerboard order parameter. So it's basically you take the densities, and I guess on the white squares you add them, on the black squares you subtract them. And if I say something wrong, which is possible, please say. Okay, so there's this checkerboard order parameter, and you can imagine that the coupling to the cavity mode, it can, depending on, say, for example, the relative phase, it can make the atoms like to be in the white squares or the black squares, yes? And that corresponds to a checkerboard order parameter of plus or minus n, I guess. And the thing is that the cavity mode, of course, has some losses, as you do. And so this is the losses kappa. And so the system is sort of kind of interesting in many ways, of course. And for us, it was interesting amongst other reasons because it's an unusual collective system, right? You have this big collective system and it's coupled to just one single dissipative mode. So in some senses, this could be considered similar to a model of a quantum measuring device. You have this big quantum system and one mode over here which has dissipation and things like this on it. And in the experiment, there was a big phase diagram found, and our investigations are along here. So in the parameter space, roughly. So there was a superfluid, a super solid in the transition region, if you like, and going to a charge density wave as the coupling between the cavity and the bosons was increased. And so it's a Bose-Hubbard model. So the occupations on the single lattice sites in the experiment were of the order of up to 5 or 6, I think, occupations. So it's not a spin half type model like a Dickey model. And we wanted to have a look at this. Now, of course, we're not the first people to have looked at this. And one of the reasons we wanted to look at this is because we're sort of computational. I don't know, we like to do numerical experiments on large quantum systems in our group. And this is sort of a difficult system to simulate because you have a large quantum system and dynamics and so forth. And of course, one of the ways that people usually look at this system is the extended Bose-Hubbard model in a adiabatic elimination approximation. So what you do, you say that, well, the dissipation is fast enough so that the cavity mode is matched to the Bose-Hubbard to the atoms, and that's the fastest time scale in the system. So if you just find the equilibrium value of the cavity mode compared to the atoms in the Bose-Hubbard lattice, then you can substitute it and you end up with a extended Bose-Hubbard model which has long-range all-to-all interactions for the system, yes? And many people have studied this and they find, for example, various predictions about the ground states, or it's not really the ground states, but the long-time steady states. So you have true long-range order in 2D, for example, apparently, and a second-order phase transition between the supersolid and the charge density wave state, for example. But we were intrigued. We wanted to see what happens when you leave this adiabatic elimination approximation. Now, of course, we're not the first people, again, to have done that, and there were some very good works by the group of Karina Kolath a couple of years back using matrix product states on slightly smaller systems and occupations of a half, right? And so they find similar physics to what was seen in the experiment. You can, if they look at, for example, you look at the Hizimi Q distribution in the supersolid state, then you see that there are these two states of the cavity mode that are indicated once you cross the threshold, and many other physical features were seen. And so they went to times of TJ of the order of 10 or 50. And so you can sort of see that after the sort of expected evolution times of TJ of order 1 or 10, you get to a steady looking state here. However, our impression was, and of course, again, I could be wrong here in a naive sort of theorist's approach, that the experimental preparation times can be much longer, of the order of 10 to the 4th or 10 to the 5 TJ from what we saw in the parameters in the papers. So we wanted to see whether this is stable, and we also wanted to look at single realizations and higher occupations, more like in the experiment. And so we know we wanted to look at this because we know we have a way to look at it. So we've been working on methods for simulating the quantum dynamics of large systems for many years. And in particular, there was a paper a couple of years back where we looked at dissipative Bose-Hubbard models without the cavity, but dissipation on all the lattice sites. And we find that in a large range of parameter spaces, for when you have reasonable high occupations or dissipation, you can actually treat the full quantum dynamics exactly using stochastic phase space methods, such as a truncated Wigner approach or a positive P approach. I won't go into the details of how they work, but basically you have trajectories in this phase space of configurations which evolve, and you can, it's very sort of convenient in many ways if you can make it work, because you get single runs which correspond in a large degree to single experimental runs, and you can do quantum dynamics of the you can do the full quantum dynamics in many situations, especially using this positive P approach, which I'll add we couldn't get to work on this system. We had to use the truncated Wigner. But the thing is, you can also simulate very large systems. So for example, this thing you can't see here for some reason is that we were able to simulate the quantum dynamics of a 256 by 256 lattice going to a steady state using this positive P method. Now, when we looked at this system using this truncated Wigner approach, here's the equations we simulate. So, all right, let me just mention what this stuff is. So we have basically a nonlinear Schrodinger equation here for the atoms in the optical lattice, which is like a Gross-Pitayevsky equation, roughly. Here we have the Gross-Pitayevsky part with tunneling. Here's the coupling to the cavity mode, and that's it. And then for the cavity mode, we have something similar, and there's a coupling to the atoms in the optical lattice plus some noise in this Wigner representation, which is related to the losses in the cavity. So you see that you have a system of nonlinear equations. Well, there's as many equations here as there are sites on the lattice, plus one equation, one complex equation for the mode, for the cavity mode, with some noise. So you see that depending on the noise, you get different experimental runs, different trajectories of this. And we can reproduce parts of the phase diagram. So if we change the strength of the coupling from the 2D Bose-Hubbard model to the cavity, then we go from a superfluid system through a supersolid to a charge density wave, which we can you can track this by looking at some different order parameters, such as superfluid order parameter, a supersolid order parameter related to like static structure factors of the system, and some and this checkerboard density parameter as well. Yeah? So that's encouraging. And now we wanted to have a look at the steady states and single runs, and also how good this adiabatic elimination approximation, which pins the cavity mode to the Bose-Hubbard model, how good is that? And so we looked at this, and one of the things we found sort of fairly quickly was that it seems like the long-term steady states of this system are not the same as what you get with the extended Bose-Hubbard model. So for example, the extended Bose-Hubbard model predicts true long-range order in the superfluid and supersolid, whereas here it seems like we have quasi-long-range order only. It decays eventually. in a parallel way. And for example, the phase transition from the supersolid to the charge density wave in the extended Bose-Hubbard model with the adiabatic elimination was predicted to be second order, but here there's indications that it's a BKT phase transition, for example. So we looked at the cavity mode away from this adiabatic elimination approximation. And what do we see? So these dots here are single runs of the simulations. And here's the real and imaginary part of this cavity mode when we're in the, I believe this is in the supersolid, yes. And so, for example, in the adiabatic elimination, there's there's a set relationship between the cavity mode and what's going on the lattice. Whereas here it's not quite as set, right? Because we allow for quantum fluctuations. And you can see that in this particular case, it's on a macro scale, it's similar, but there's some deviations. So the full model's runs are in green or turquoise or whatever. And then if you zoom in, then the adiabatic elimination approximation assumes just things on a single line. Now, one of the things that was really different in this case, getting to the end, is that when we look at long times, this was the region that's reached at sort of what seems like long times by these matrix product state simulations, but in fact it's a metastable state. If you go for really long times comparable to supposed experimental preparation times, you actually jump to a different steady state, which differs in some features from this one, which we're still trying to investigate the details of. And perhaps the most interesting feature of this is that if you look at single runs, and this is the case often when you look at single runs of a large system, it turns out that the mean doesn't correspond to what happens in a single run very well at all. So for example, if you look at the mean over these times, here's the mean checkerboard order parameter modulus, and so it goes up and then it has a long transient decay and a steady state. But in fact, the steady state, if you look at single runs, is it jumping up and down between the different checkerboard configurations, yes, which are macroscopically very distinct, at least in terms of this checkerboard order parameter. You can actually but there's probably no time I'll show this while we're talking. So going to conclusions, our conclusions are we can successfully simulate very large systems of this kind. So there were lattices of say 64 by 64 in these runs, and the long-time steady states are not the same as what the extended Bose-Hubbard model predicts. And we want to understand what's going on. What's the mechanism for this switching? And also, we want to try and introduce some imperfections to the model. So there could be more cavity modes, which are sort of minority or non-uniform background as well. Here's the team, 2 people from my group and these 2 guys. And let me just run this while we're... You'll see this jump over here. Thanks very much.
Thank you. Yes, I think we have time for a quick question. And yes, please.
Thank you. Very nice, inspiring. A question, I might have missed it. Is that with or without trap, or could it be made?
It's easier to make it with a trap, but this was with no trap. That was one of the things we want to look into now. Yeah.
Okay. Thank you.
I'd be happy to talk about. Stuff.
Thank you. Yeah. Let's do that.
Yes, and may I ask how sure you are about the nature of the phase transition from the supersolid to the charge density wave?
So
you go from one approximation to another in the changes.
Yeah, there's 2 answers to that. So 2 parts to the answer. One is we looked at the details of it pretty well, or Giuliano looked into them pretty carefully. So inside the model, we're pretty sure. But then the question is the truncated Wigner a good model? So the referees sort of pressed us a lot to benchmark this model. And of course, you can't sort of actually do it using a different method for these very large systems. But we did, I have a slide on this actually. Where is it? Yes, so we looked at the accuracy of this truncated Wigner model compared to quantum trajectory simulations on small lattices, 2 by 2, 2 by 3. And we see that the discrepancies decrease very rapidly as you go to larger sizes of the system, at least in the observables we looked at. So it seems like it's probably legit.
Okay, thank you.
Thanks.
Yes, so maybe let's applaud again and move on. Thank you.